All right, folks, this is going to be part 2 on a recording here that I'll post after the fact because apparently we lost internet here on campus. Sorry for the trouble. You'll have 2 videos this week and should be okay. All right, so all this nonsense of looking at... Oh, yep, sorry, I got to flip the screens here. Thank you. All right, make sure I'm on the right screen here for in the room. So finding the maximum depth of a tree rooted at a given location is a little rough. This is not ideal here. And doing that is really slow. So a better way is, instead of calculating based on the depth here, we want to go through and say, hey, I want to check the height of the children in my children list here. And we're going to start adding those together here. So the maximum height of each of my children plus 1. This way I don't need to go through every single value and find every position, look at whether it's a leaf or not, and then get the depth of that and have to run again here. We're just going to calculate height going upwards, which essentially is how we did our depth. We just ask for a parent, ask for a parent, ask for a parent. We'll just go through each of the children and just add 1 for each level that we have. So this one's going to be a little faster for us going this approach. So we can say, hey, I need the height 2. I think we can steal almost all of this here. Oh, it's not going to copyright. Copying out of the book's obnoxious. Yep, that is awful. Forget that. Forget that. So this is our get height better. I mean, we'll just call it just get height, right? Because this one's just going to work a little better here. So for this one to work, if we're a leaf, we're 0, right? So if self.isLeaf, we're just going to return 0 because there is no more height on this one. We're done here. If we're not a leaf, then we can return 1 plus, and now we want each of our children to go do the same thing. So you can do this fun list comprehension thing all in one line, which is a little messy here, but you can do this. So we want the max of the self of get height of the child, right? I don't like how he uses all his books here, or all these shorthands here, for self-children. So this is going to add up 1, similar to our other approach, right? So we should be able to use get height, and this should be faster for us here. Too many new lines in between. Okay. And let's see if this works the same way. So with the height of the bad height of and a good height of tree dot get height. Let's see if this works for us. Oh goodness, we crashed. Oops. Tree get height takes 1 argument, but 2 were given. Get height? Oh, we don't need get height of the child. Why are you passing the child for a given position? That's right, we don't need to. This is child. Dot get height. Or we're not using the positions. We should be able to do child get height for each child in self-children. Try that again. Right. And now this is actually calculating a little bit more what we'd expect when we look for height given a specific root. Right? It's not going down and asking the depth, which works all the way back up to the parent, where this is sure technically correct, but it's not for the tree rooted at this location because it goes past that. So now our height and our depths are inverse, which is what you'd expect. When you have no more children, your height of 0 is 0. We're properly calculating this here. When you have no more children, your height is 0, right? But the depth then is how many levels do you have up to the top. So now we're getting a better result as well, and it's going to work a lot faster for us, which is much prettier. We can get rid of this bad one here. Or I guess we can just leave it in. That should be okay. So again, this one was easy. Doesn't mean it's right. Anytime we're dealing with recursion, right? Sometimes it's easy, but it just doesn't work well. So thinking about the better approach is tricky sometimes. And then I mentioned one of the specific types of trees we're going to look at is a binary tree. And a binary tree makes life a whole lot easier for us because it's not n number of children. You just have a left child and a right child, or no, like up to 2 children is the most children you can have. So we're kind of restricting the shape of this tree here. And these are super useful for all sorts of things we're going to get into later on. We'll use binary trees to do lots of things later. So these are pretty handy. And it's easier to implement the binary tree because you only have a left and right. So if you want to get all of my children, I can give you my left or I can give you my right. I don't have to loop through a whole list and collection of children there. But again, he builds each of these off of these abstract classes, which I find confusing. So I will try not to do that. That might also be confusing because I'm not following the book, and I haven't found a good solution for that. I'm sorry. But I think his is more confusing. Is that okay? All right, so it's a little awkward. So interesting stuff about binary trees, though, which is really interesting. So if you look at the level here of each generation and how many nodes there are in each one, notice they follow the power of 2. Right? You have 1 node and then 2 nodes and 4 nodes and 8 nodes and 16 nodes and on, because if each one has 2 more, right, you're doubling every time. That's a quick double. We follow the power of 2. And then the total number of nodes, right, that also follows this then. So if you have at level 0 and at level 1 and at level 2 and at level 3, right, you have 1 node and you have 2 nodes and then you have 4 nodes and you have 8 nodes, right? In each one of these, the total number is the next power of 2 minus 1. Right? So then total is 1. Total is going to be 3, right? 1 plus 2 is 3. The total here is going to be 7. 1 plus 2 plus 4, right? And then the total here, when you add more, is 15. So the total number of values that you can store, right, is your next power of 2 minus 1 when you follow this binary tree format. Hey, I think we got the internet back. The thing just loaded on the other computer. That is crazy. I feel bad for the IT support people. Anytime the internet goes down, it's just a bad time for everybody. So anyway, so you can see quickly, you start increasing the number of values you can store very quickly, which is nice. But you can calculate pretty easily how many you have at each level, how many nodes along in here, right? So all sorts of math. The book loves math. Honestly, I'm not that fond of it, but that's okay. The math is important, right? So you can write trees. So this linked structure for trees, right, where you know what your parent is, like we did with our end tree. We know what the parent is. We have a link to it. We're directly pointed at it. And then we have our link to all of our children. We know what all our children are. In our list of children, we have links. Right? We just reference where they live in memory. And then we have the actual item. So same idea with this. You have a link to your parent. You have a link to your left child, a link to your right child, and then the actual item that you store somewhere else in memory. Right? What's the real value? So we're storing a lot of information here just to store one piece of data and relate it to the other one somehow, but it works. So different things we can do. Trees are fun. The performance of them is pretty quick, which is nice. So we can track length. We can track if we're empty or not. To get any individual link here is constant, but that's only your link up, your link down left or down right. We're not giving you everything in the tree, but if you know where you are in the tree, I can give you my parent relation or my left child or my right child really quickly, right? Going to calculate the depth, right? It's going to be, we just have to walk up how many parents we have for that. The height then is still n. We have to look at all n things to find out what our depth is. But it still performs pretty well, which is nice. And then adding given things is fine. The other cool thing you can do with binary trees is you can store them in an array, right? Only because they're binary trees. So the idea with a binary tree, if we want to store them in this array-based storage, right, where we have, let me do this in Word here, it's probably easier. Let me just draw a little picture. So if we have this tree and I have, here's a mammalia, and then we have carnivores and felines or something like this, right? Sure. If this is the root of my tree, if I make an array-based storage location here, the first item here will be mammalia, and then the next 2 slots will be my children here. So then I have canines and felines. If they have children down here, right, if we had specific dogs and cat breeds here, the next 2 spaces will be for the canines here, and then 2 more for the felines. So you get 1 item here, you get 2 items for the next level, you get 4 items for the next level, and then you get 8 items for the next level. So you can kind of imagine squishing this tree form into a list because you know based on what level it is where it goes. Does that make sense? How we can find, we just slot this many spaces here. So this array then, if I have more children, right, will have more spaces. I'll just double the number here. So the next 8 spaces. So this is level 0, right? This is level 1, level 2. So this gets 1 space, this gets 2 spaces, this gets 4 spaces, right? The next level will get 8 spaces, and we just jam them all in the array. So the first thing, the next 2 things, the next 4 things, the next 8 things, the next 16 things in that big array storage, that list storage, just get thrown in there. There's actually some easy math you can do to find out what index you need to be at here. Where do did he give us the index? Did not. Okay, that's fine. Implementing tree traversals, that's fine. Okay, this is the stuff we need. This yield keyword is what we're looking for. Yield is really neat. It will pause and wait. So if you put something in one of those for loops, you want to say for item in some collection, yield lets you give back an item, and it remembers where it was, so that when you come back to the next item, you can yield it again. So we'll work on actually yielding these items in lab. It's a good exercise as we build one of these out. So we'll build a linked version, and we'll build an array-based version in lab. It's really boring. I'm sorry, but it's a good exercise for lab. And then you'll see that you can iterate over all the positions and give you all the positions here. Works out pretty well when you're doing these traversals here. Yeah, and then he's got some applications. So the arithmetic for what your index is for your given level here, right? So you need to find what the depth is of your location, and then we can do some quick arithmetic to find out what index you're going to be in based on if you're the left child or the right child. So we'll say it is your depth, right, divided by 2, and we want that integer floor division, right, because this will round down for us. And we want an integer result. So your depth divided by 2 is going to give us some information. So at depth of 0, right, we divide by 2, you're at index 0. That's pretty quick. Now, at depth of 1, I think you need to multiply this. At depth of 1, then we need to see if you are a child somewhere, because if you're a left child of something, right, of your parent, then we're going to add 1. If you're a right child of your parent, we're going to add 2. So we're going to say plus 1 for left children. Left. Sorry, I don't have my mouse here. This is really ugly. I didn't even bring my tablet. Right, and we're plus 2 for right. Right. Oh goodness. Hey, that G was pretty. Right. So at level 2, no, it must not be divided by 2. I don't remember the arithmetic off the top of my head. I'll have it for you when we do lab, because we'll write what this actually is. So you can say, for any given level, what index should you be at here? So we know that this is index 0, 1, and 2. So starting at 3 through 7, right, is going to be where my next 4 values go. Right? And then for indexes 8 through 14, that'll be my next 8 indexes for those children. So you can do the arithmetic. I'll have to look that one up here. I thought he had it in this chapter, but I don't see it right now. I think it's later, right, when he actually goes and implements the tree. What's he have here? Yeah, he doesn't actually give you the implementation. He just gives you the structures here. So yeah, array-based implementation, doesn't he have that? I think he just gave us what it looks like as an abstract class. Implementing linked. Yeah, array-based. Oh yeah, right here. So if P is the left child of a position, then it's 2FQ plus 1 or 2FQ plus 2. Okay. So yeah, our level number. Okay, yeah, this is what it is here. So the arithmetic for where it needs to go. hate reading math sometimes, sorry. 2fp plus 1, 2fp plus 2, and the parent has the index of the floor of f of p minus 1 divided by 2. We leave the details of a complete implementation as an exercise. Here you go. It's an exercise for us. So we'll do this one in lab. We'll actually write it out here. This looks really ugly, I'm sorry, but it's not too bad, I promise, once we actually look up what the code is. Does that make any sense? Or is it gibberish? It's a little gibberish. Okay. Once we look at the actual code for it, it's not too bad, I promise. So we just need to find what the index is of our parent. There we go. So we double our parent's index. That's what it is. Double our parent's index. Right? So whatever the index is of our parent, we double it, and then we add 1 or 2 if we're left or right. There, okay. So the index of our parent, that's okay. So forget that. So it's the index. This is awful, trying to do this with a trackpad, of our parent. I can't even, can I just type, I can just type in here, right? Index. Nope, I want to type over here. All right, I'm failing at this, I'm sorry. We'll do it in lab though, promise. Does that sound like an easier formula? Get the index of your parent, double it, and then add 1 or 2? So the only one that we need to know is if you're the root, your index is 0. That's it. So the index of this one, what's the index of my parent plus 1, or the index of my parent plus 2 is from my right child. And I know my parent's index. So we can quickly work our way up that tree to find what the index of our parent is. We'll work out pretty quick. Yeah, because we will actually have to write that out when we build our tree. So this is really a linked tree and a linked n tree with n children. So we'll write a linked binary tree and a array-based binary tree for storage. So the array-based storage makes sense if our tree is relatively full. So an interesting, what a valid tree is, here, let me go add another page. So it's possible to have a tree that looks like this, right? 1, 2, 3, 4, 5, right? Is this a tree? Technically, yes. It's ugly, and it's a really badly shaped tree here, but if we were to store this sort of tree in an array-based storage, we'd have 1 level, 2 levels, 3 levels, 4 levels, 5 levels, 6. I just counted up to 6. 6 levels, right? 2 to the 6 number of positions in an array for storing 6 things. That's not ideal at all. If this were a linked-based tree, right, we would have, and specifically look at binary trees, right, where you have a left and a right. We're going to store no parent and a left and a right, parent left 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 right. That's only like 3 things for each of these. That's 18 items instead of 35 items. So the linked storage works out to be more memory efficient if our tree is in a weird form like this. So one of the things when you talk about trees, and binary trees in particular, you can be a full tree or a complete tree. And I never remember which is the difference here. So binary tree, full versus complete. Look at that. Geeks for geeks. They're probably good here, right? So a full tree is, no thank you, I don't want to log in. A binary tree in which you all have 0 or 2 children. So every level is completely full up until the last level. So if you have 1, 2, 3, this is a full binary tree because every level has all of its children except for the last level. If you were to add another child over here and say this is 4, you're no longer a full tree because now you have 1 child at one level and 0 children at another level. That's no good. Right? Or over here, if we had a 5, again, this is still not a full tree because not every level has all of its children up until the last level. Right? This 3 over here has no children, so we're no longer full. What you have here, though, this is known as a complete tree. So if it's complete, it's a full tree. Complete. P-L. Really need my mouse back. I'm sorry. I wonder if I could just steal this one. A complete tree is full up to the last level, and then at the last level, everything is there from the left on. So as you start adding more children, you add them at the leftmost position, the leftmost position, the leftmost position. So as you start filling up this next generation, we're still complete. We're still complete. If we were to add 8 over here, we'd still be complete. But if I jump over here and add 10, we're no longer a complete tree because this child over here is missing. So this is not complete here, and it's not full. So complete trees work really well in array-based storage, very efficiently, because you're filling up every level as you go. So you don't have those big gaps of, hey, I'm missing 1 item here, and I'm missing 3 items here, and I'm missing 7 items here, I'm missing 15 items here, and I'm missing 31 items here. Right? You don't have this giant gap of storage because you're filling everything at every level. So complete trees, full trees fit very well in array-based storage. Ones that aren't full and complete don't. And later when we get to some more of this interesting stuff with tree structures, trees have this cool ability to, or specific trees, sorry, search trees specifically can reshape themselves. Because search trees will have a particular format we'll talk about. They can resize themselves so they don't look like this big, long, ugly chain here, but they make themselves more balanced, where you have basically close to the same number of children on the left as children on the right. Imagine like it's one of those like weighing scales, like this, what is it, the scales of justice or something that balance. It tries to auto balance itself in particular formats. So you can't do it with a generic tree because the order matters. But when we talk about search trees where they have a very particular format, we can start balancing these things out. So we'll use linked versions, and then we'll get to array-based versions when we go. And our priority queues take advantage of being a complete binary tree. So we can store it in an array very easily here when we start talking about priority queues, and they follow a very particular set of rules as well, which is interesting. So that's a lot of fun when we get there. So when we do our lab, we'll look at implementing the linked tree. That one's mostly copy-paste, and we have most of it already, but we're going to do the binary tree format, where we just have a left and just have a right, because then I can actually traverse through these things, and it'll work a little nicer for us. And then we'll also look at the array-based storage with that quick little arithmetic. What's my parent's index? Double it, and add 1 or 2. And then we'll move on to priority queues. These are a lot of fun. Priority queues are really cool. So like a queue, first in, first out, the priority queue is not first in, first out. It's highest priority, out first. So you get to define that. So imagine the typical example, there's the emergency room. Right? If you go to the emergency room and you've got a bad cough, someone who has a heart attack is going to go in ahead of you, right? That's just, you want the highest priority to go first. So we can have a structure that allows for that sort of thing. And basically we tell it, how do you want to sort these things? A lot of times it's, the highest value will be the new next value, or the lowest value be the next value. And we can just define that, which is a lot of fun when we do priority queues. I think in terms of trees, so we did the depth first traversal. There's a couple other traversals you can do here. The breadth first, right? We did the generation by generation by generation. That's the breadth first traversal. We did that one, and we did the depth first. The in order traversal, you have to do a binary tree. We don't have a binary tree yet. So in order doesn't really make a lot of sense until we get to actually having a binary tree specifically, because you'll do a specific order for these in order traversals here. It works out pretty well. And then, yeah. Again, we're kind of just scratching the surface of some of these ones. We're not getting in super deep as we go, because you're going to hit these topics later in the data structures algorithm analysis class. So we're going to talk about trees, understand some of their basics here. We don't need to get into all the advanced stuff. Same with priority queues. We'll do maps. We don't really worry about hash tables and skip lists. We'll talk basic search trees, basic sorts and selections. You'll hit all the advanced stuff later on. So we try and intro the topic, so when you come back to it later, it makes a little more sense. That sound good? All right, cool. How's the next project feeling for you? Did anyone get started on it? I know we got a lot of time, so not too big of a deal here. And then I was going to give you last year's midterm today, so that you can actually look at the questions and give them a chance to try them yourself. And then when we come back on Tuesday, the 21st after lab, I'll go over answers to them. So let me go grab that out of Canvas, assuming the internet's working again. If the internet's not working, we're not going to have much luck with that, because I don't think I have it in PDF form currently. No, it is not working. Okay. I will post that for you later then when I can get internet access. Is that okay? So again, it's half quiz questions. So I did post the linked list quiz. Thank you. I'm literally using, oh, they're loaded. The same question bank. I'm just going to use those exact same questions. So go look at the quiz. If you haven't, you should be able to see the answers on all the quizzes. If you don't, let me know because I probably set it up wrong. But I think I should have set them all up so you can see answers to quizzes. And if not, I just screwed up on that. Yes, I said yes, log in. The internet's just super slow, so I will post that for you later. You don't have to watch me make a PDF out of the last quiz, the last midterm. So no plan to meet on the 23rd, right? The midterm will open 2 p.m. on the 23rd. As long as you get it in by 2 p.m. on 3/7, we're good. So ideally, you just sit and take it and you're done, and you can have a winter break. Again, totally up to you, however you want to manage your time. I'm open to whatever works best for you. So, and we can go from there. So it is open notes, open internet, open book, not open person. Right? It's your work. If you go find something, great. Cite your source. That's perfect. Don't go ask anybody. I had someone post the questions on Chegg, and they're like, "Hey, look, I cited my source. They're on Chegg." Like, no, it's not how this works. It's not how any of this works. But they're like, "Yeah, I cited my source." Okay, I don't know. So you don't need to hear me whine and complain about that. So, all right. So I'll stop the recording now, and then I'll post this recording for you folks later. Sorry for the internet trouble. Eventually, we'll figure out our Wi-Fi here. Oh, look at that. I wasn't even on the camera. That's fine. All right.